keeps on going, and we're all going to freeze to death until we solve the mystery of dark energy. We do not know the ultimate fate of the universe.
The ultimate goal of cosmology contains the greatest ambition of any scientific field: to understand the birth, growth, and evolution of the entire universe. This includes every particle, antiparticle, and quantum of energy, how they interact, and how the fabric of space-time evolves alongside them. In principle, if you can write down the initial conditions describing the universe at some early time, including what it's made of, how those contents are distributed, and what the laws of physics are, you can simulate what it will look like at any point in the future. However, in practice, this is an enormously difficult task. The visible universe, what is visible when we look at the stars, planets, and galaxies, only represents 5% of the universe. The other 95% is made up of matter and energy that we do not know. This is a big question mark for us, and that is why we call it dark matter and dark energy. These dark forms of matter and energy do not directly interact with our instruments, such as telescopes, for example. Put simply, they are completely invisible. Although the exact nature of dark matter and dark energy is still unknown, their existence has profound implications for the fate of the universe. That's why scientists are extremely eager to decrypt the mysteries of the rest of the universe. But how do you study something that can't be seen, touched, or heard? Well, Europe's new Euclid telescope may have just the solution to this problem. The ambitious Euclid infrared space telescope is on its way to decoding the secrets of dark matter and dark energy. Most recently, the Dark Universe Telescope just revealed its first sparkling images of the cosmos, marking the beginning of the quest for the very nature of dark energy. Join us today as we dig deep into the first stunning images from Europe's new $1.4 billion space telescope that paves the way for decoding the secrets of the universe. Welcome to EYES 200M, where we explore the fascinating world of science, technology, and the universe. If you're new, welcome, and don't forget to hit the subscribe button and click the bell icon to make sure you never miss out on any future interesting updates from us. Every second, millions to trillions of particles of dark matter flow through your body without even a whisper or a trace. This ghostly fact is sometimes cited by scientists when they describe dark matter, an invisible substance that accounts for about 85% of all matter in the universe. Unlike so-called normal matter, which includes everything from electrons to people to planets, dark matter does not absorb, reflect, or shine with any light. It is, well, dark. But if we cannot see dark matter, how do scientists know it is there? Well, the answer is gravity. Astronomers indirectly detect dark matter through its gravitational influences on stars and galaxies. Wherever normal matter resides, dark matter can be found lurking unseen by its side. The first real evidence for dark matter came in 1933, when Caltech's Fritz Zwicky used the Mount Wilson Observatory to measure the visible mass of a cluster of galaxies and found that it was much too small to prevent the galaxies from escaping the gravitational pull of the cluster. Something else, concluded Zwicky, was acting like glue to hold clusters of galaxies together. He named the substance Dunkle Materie, or dark matter in German. In the 1970s, Vera Rubin and Kent Ford, while based at the Carnegie Institute for Science, measured the rotation speeds of individual galaxies and found evidence that, like Zwicky's galaxy cluster, dark matter was keeping the galaxies from flying apart. Other evidence throughout the years has confirmed the existence of dark matter and shown how abundant it is in the universe. In fact, dark matter is about 5 times more common than normal matter. The universe is hitting us over the head with evidence of dark matter, says Phil Hopkins, professor of theoretical astrophysics at California Institute of Technology, or Caltech. Whether it's in the motion of galaxies, or the fact that dark matter bends light, or the expansion of the universe, or the growth of structures in the universe, there are many different types of measurements that have been made, and every single one of them fits the same paradigm of dark matter, he said. Yet, despite its preponderance, scientists have not been able to identify the particles that make up dark matter. They know dark matter exists, and where it is, but cannot directly see it. Since the 1990s, scientists have been building large experiments designed to catch elusive dark matter particles, but they continue to come up empty-handed. What some still consider the leading candidate for dark matter, called WIMPs, weakly interacting massive particles, have not been found in any of the data collected so far, nor have particles called axions. Both WIMPs and axions are hypothetical elementary particles proposed to solve outstanding theoretical mysteries in the widely accepted model of particle physics, called the Standard Model, which classifies all known elementary particles and describes 3 of the 4 known fundamental forces: the electromagnetic, weak, and strong interactions, leaving out gravity. Additional dark matter candidates include particles called sterile neutrinos, along with primordial black holes. Some theorists have proposed that modifications to our theories of gravity might explain away dark matter, though this idea is less favored. And in the past decade, another set of dark matter candidates has emerged and is growing in popularity. But despite decades of efforts, conclusive evidence is still lacking. Scientists hope that with increasingly advanced technology, one day we may find dark matter and definitively solve the mystery. And that's why Euclid was born. Euclid is a space telescope that will observe the universe at infrared wavelengths. Its primary goal is to map the geometry of the dark universe, which is made of dark matter and dark energy, hence its name, for the Greek astronomer who dreamt up the foundations of modern geometry in the 3rd century BCE. Euclid's wavelength range is 1.1 to 2 microns, firmly in the near-infrared realm. As a relevant aside, the Webb Space Telescope also images at near-infrared wavelengths, but is looking for very different things. The spacecraft has 2 scientific instruments, a visible light camera, or VIS, and its near-infrared camera and spectrometer, or NISP. Its image quality will be at least 4 times sharper than ground-based surveys of the sky, according to the European Space Agency, or ESA. The telescope will observe billions of targets that are seen as they were 10 billion years ago. Its imagery will cover over 1/3 of the sky beyond the Milky Way. Euclid, on the other hand, will look at all types of gravitational lensing, from the strong lensing that produces mesmerizing Einstein rings to the weak lensing that distorts distant galaxies, to better understand the properties of dark matter. A recent study of Einstein rings boosted the case for a type of axionic dark matter, or dark matter that behaved like a wave rather than a particle. Euclid will also look at baryonic acoustic oscillations of the universe, or bubbles of dense particles that rippled outwards in the first 300,000 years following the Big Bang. That sounds like a long time, I know, but it was actually the infancy of our universe. Studying how these bubbles emanated outwards will clarify the rate of the universe's expanse over its nearly 14 billion year existence. The ultimate object of Euclid's observations is to take data on distant cosmic sources that help explain the properties of dark matter and dark energy. Besides pulling back the curtain on the nature of these unknown aspects of the universe, Euclid's data will help scientists understand the cosmic web, or the superscale structure of our universe, from the shape and spatial orientation of galaxies to the distribution of mass across the cosmos. With Euclid, scientists can tinker with the biggest outstanding questions of astrophysical science. Why is the universe expanding? When will it stop expanding? What particles in the universe have we not yet detected, and why? What is the ultimate fate of the universe? And so on, and so on. So many questions. Launched on July 1st from Cape Canaveral in Florida, now the dark explorer Euclid opens its eyes on the cosmos. And the mesmerizing results indicate that the Space Telescope will achieve the scientific goals that it has been designed for, and possibly so much more. When the instrument was first turned on, the Euclid team found an alarming light pattern contaminating the images. According to the same release, the team realized that sunlight was sneaking into the spacecraft. By imaging at different angles, the scientists found that the problem can be mitigated. The VIS images also included cosmic rays, seen as lines across the images. Science images now from the telescopes will be artifact-free. The NISP test images showcase how Euclid will determine the distance of galaxies and their distribution through the universe over time. These data can be used to create a 3D map of the universe, showing how the whole shebang evolved. We've seen simulated images, we've seen laboratory test images. It's still hard for me to grasp these images are now the real universe, said Nud Janke, a NISP instrument scientist, in the ESA release. The images are reminiscent of the James Webb Space Telescope's test images, which were released in May of 2022, several months after commissioning began and 2 months before the telescope's scientific programming commenced. The infrared images are seen in orange, as the images have not gone through image processing to represent their cosmic scenes in representative color. The NISP image included above is only 4% of the instrument's field of view. The image was produced from a 100-second exposure by the telescope. During regular operations, Euclid will collect light for about 5 times longer, indicating that the recent test image is just a small taste of the observatory's capabilities. In the same fashion as Webb's timeline, Euclid's first scientific images won't come along for at least a few months, as the ESA team works to ensure that the telescope is performing optimally. The effort to understand dark matter will undoubtedly define much of astronomy for the next 2 decades. Astronomers may not know what dark matter is, but inferring its presence allowed them to pursue, in a new way, an eternal question: what is the fate of the universe? But to understand the fate of the universe, we have to look back on its past. The Big Bang marks the starting gun of the greatest race of all time, between gravity and the expansion rate. Which one will eventually win in our universe? Well, the answer to that question, the classical reasoning went, should determine our universe's fate. Here's what we thought the possibilities were. Number 1, the universe recollapses into a big crunch. The expansion starts out rapidly, and the large amount of matter and radiation work to pull everything back together. If there's more than enough matter and energy, the universe will expand to some maximum size. The expansion will reverse to contraction, and the universe will recollapse. Number 2 possibility, the universe expands forever, resulting in a big freeze. Everything starts out the same as above, only this time, the amount of matter and energy is insufficient to counteract the expansion. The universe keeps expanding forever, as the expansion rate keeps dropping but never reaches 0. And number 3 possibility, the universe expansion asymptotes to 0. Imagine the borderline situation right between the above 2 examples. If there were 1 more proton, we'd recollapse, 1 fewer, and we'd expand forever. In this critical or Goldilocks case, the universe expands forever, but at the slowest rate possible. To know which possibility was correct, All we had to do was measure how fast the universe was expanding, and how that expansion rate changed over time. Physics would determine the rest. It was one of the greatest quests of modern astrophysics. Measure the rate at which the universe was expanding, and you know how the fabric of space is changing today. Measure how the expansion rate has changed over time, and you know how the fabric of space changed in the past. Put these two pieces of information together, and the way the expansion rate both is and also has changed allows you to determine what the universe is made out of, and in what ratios. To the best of our knowledge, informed by these measurements, we've determined that the universe is made out of about 0.01% radiation, 0.1% neutrinos, 4.9% normal matter, 27% dark matter, and 68% dark energy. This quest, which began as early as the 1920s for some, got an unexpected answer in the late 1990s. So, if dark energy dominates the expansion of the universe, what does that mean for our fate? Well, it all depends on how, or if, dark energy evolves with time. Here are the 5 possibilities. Number 1. Dark energy is an expansion-dominating cosmological constant. This is the default option given the best data we have today. While matter becomes less dense as the universe expands, diluting as the volume expands, dark energy represents a non-zero amount of energy inherent in the fabric of space itself. As the universe expands, the dark energy density remains constant, causing the expansion rate to asymptote not to zero, but a positive value. This leads to an exponentially expanding universe, and will eventually push away everything that isn't part of our local group. Already 97% of the visible universe is unreachable under these conditions. Number 2, dark energy is dynamical and grows more powerful over time. Dark energy appears to be a new form of energy that's inherent to space itself, implying that it has a constant energy density. But it also could be changing over time. One possible way it could be changing is that it could be strengthening in magnitude, which would cause the universe's expansion rate to speed up over time. Not only would more distant objects appear to accelerate away from us, they do so at an increasing rate. Even worse, objects that are now gravitationally bound today, like galaxy clusters, individual galaxies, solar system, and even atoms, would all someday become unbound as dark energy strengthened. In the final moments of the universe, subatomic particles and the fabric of space itself would get torn apart. This big rip, if you will, fate is a second possibility. Number 3, dark energy is dynamical and decays over time. How else could dark energy change? Instead of strengthening, it could weaken. Sure, the expansion rate is consistent with a constant amount of energy belonging to space itself, but this energy density could be dropping too. If it decays away to zero, it could lead to one of the original possibilities expressed above, the Big Freeze. The universe would still expand, but without enough matter and other forms of energy to recollapse. If it decays away to zero, it could lead to one of the original possibilities expressed above, the Big Freeze. The universe would still expand, but without enough matter and other forms of energy to recollapse. If it decays away to become negative, however, it could lead to another of the possibilities, a Big Crunch. The universe could be filled with energy intrinsic to space that suddenly switches signs and caused space to recollapse. While the time scale for these changes is constrained to be far longer than the time since the Big Bang, it could still occur. Number 4. Dark energy could transition into another form of energy, rejuvenating the universe. If dark energy doesn't decay, but instead remains constant or even strengthens, there's another possibility that arises. This energy, inherent to the fabric of space today, may not remain in that form forever. Instead, it could get converted into matter and radiation, similar to what occurred when cosmic inflation ended and the hot Big Bang began. If dark energy remains constant until that point, it will create a very, very cold and diffuse version of the hot Big Bang, where only neutrinos and photons can self-create. But if dark energy increases in strength, it could lead to an inflation-like state followed by a new, truly hot Big Bang once again. This is the most straightforward way to rejuvenate the universe and create a cyclic-like set of parameters where the newly created universe gets another chance to behave just like ours did. And finally, number 5. Dark energy is related to the zero-point energy of the quantum vacuum and will decay, destroying the universe we know. This is the most destructive possibility of all. What if dark energy isn't the true value of empty space in the lowest energy configuration, but is the result of symmetries early on in the universe having broken into a false minimum configuration? If so, there would be a way for it to quantum tunnel into a lower energy state, changing the laws of physics and destroying all bound states, or particles, of quantum fields today. If the quantum vacuum is unstable in this particular way, wherever this decay occurs will result in the destruction of everything in the universe in a bubble which expands outward at the speed of light. If such a signal ever reached us, it would be accompanied by our instantaneous destruction too. And so, although we do not know which of these possibilities is true for our universe, the data is incredibly consistent with the first option, of dark energy truly being a constant. Right now, our observations of how the universe has evolved, particularly due to the cosmic microwave background radiation and the large-scale structure of the universe, place tight constraints on how much wiggle room there is for dark energy to change. If dark energy offers any indications that our fate will be different from the one we anticipate today, Euclid will be the one with the best chance to scientifically reveal this new truth about our universe. Until then, all we have are the possibilities we know to consider. The rest is up to science. Well, that's all the information we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit that bell so you never miss out on future episodes. And be sure to tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we'll see you next time.